Hello, in this one we're going to make use of series and graphs in 3 dimensions and variable substitution. We're going to glue it all together and explore how to write a series for, say, a slice of a 3-dimensional graph. So imagine that our function z equals e to the negative, and then here it says x squared plus y squared. We're beginning with that. Now, just by knowing that I have a root of x squared plus y squared, I can remember back the following, that r squared equals x squared plus y squared, which implies that r itself equals x squared plus y squared. And that allows us to rewrite the function now as simply e to the negative r. But let's stop right here and let's make a picture of all of this. Remember, my channel is called Visual Math because sometimes I draw a lot of pictures all the So I'm going to do it this way. This is going to be my x-axis over here. And then here this is going to be my y-axis, and this is going to be my z-axis. So now let's make a picture of e to the negative square root of x squared plus y squared. I've done that and I know what it looks like. So I'm just going to do it pretty quickly. This is how it looks in the xz plane, roughly speaking. This is how it looks, roughly speaking, in the yz plane. And then it intersects the xy plane roughly like that. That's not too important. How do we picture this variable substitution step? So r squared equals x squared plus y squared, and then so r by itself equals the square root of x squared plus y squared. Clearly that's just another application of the Pythagorean theorem, so that's going to look like this. Imagine we have a new axis coming out that way. This will be called the r-axis in this context. And let's actually show the transformation. When I zoom in, I can imagine that this is basically x and this is basically y. And then this portion right here, that represents r. So this is how far you're going along that axis using x and y. So you're converting from rectangular coordinates x and y basically to a coordinate system that looks like this, polar coordinates, as you might remember. So then you have basically a new number line that looks like this. You're measuring that along that number line. Let's now do a slice above this number line and then through the surface. If I do that, roughly speaking, it will look like this. So what does that mean? Well, take a look. Imagine that r is a particular value. I'm going to call that r sub 0. So imagine that that's that value. When you plug it into your function, what it's going to give you is e to the r sub 0 with a negative out front. It's simply the value of the z coordinate at r sub 0. That's all it is. So for example, when r has the value 1, e to the negative first would be the value of the z coordinate at that point. If r has the value 2, then e to the negative 2 would be the value of the z coordinate at that point. It's how high you are above the xy plane. That's all it is. Now, because we do have e to the negative r involved, you might ask yourself, would it be possible to do a series representation of that green curve along the surface? And the answer is yes. Let's do that. So I've turned off the grid and I've given myself some space on the bottom because I want to now do some additional calculations. Remember this fact that e to the x, which is the basic exponential, is equivalent to writing this. In terms of its series, it's from 0 to positive infinity of x to the n over n factorial. But this is a general kind of relationship. So in other words, if I wanted to represent e to the negative r, I could simply replace x with negative r. So in other words, I would now have a series that looks like this. N from 0 to positive infinity of negative r to the n over n factorial. Let's do this. Let's write out, say, 3 or 4 terms explicitly. So for example, imagine that n has the value 0. I'm going to zoom in here so we can see everything better. When n has the value 0, the first term would be negative r to the 0 over 0 factorial. Next one. Imagine n has the value 1, and this would be negative r to the first over 1 factorial. Next one. Imagine n has the value 2, then this would be negative r squared over 2 factorial. Imagine n has the value 3, then this would be negative r cubed over 3 factorial. And then imagine after that plus dot 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 ellipses, meaning we just continue. Remember that since we have infinity up here, it's an infinite one. So what I'm going to do is just chop off anything after the n equals 3. That's going to generate 4 terms. Now let's actually understand what this is telling us. Let me just simplify these. So I'm going to chop off anything after n equals 3. So when I do this one, it's going to be negative r to the 0, which is 1. 0 factorial is 1. 1 divided by 1 is 1. This gives me a value of 1. Then I add to it. Next one is negative r to the first is negative r. 1 factorial is 1. So that gives you negative r. So here you put plus negative r if you like. For the next one, you're going to have negative r squared over 2 factorial. Negative r squared is positive r squared, and 2 factorial is just 2. So that's going to generate a new term. That term looks like plus r squared over 2. Let's do one more here. So negative r cubed becomes negative r cubed, and then 3 factorial is 3 times 2 times 1. That's 6. So that's going to generate one more term that says negative r cubed over 6. So this right here is an approximation to the value of e to the negative r using only the operations. Think about it. Addition, subtraction, exponentiation. That's about it. And exponentiation is really just multiplication. That's why we have series, right, in a certain sense, because then all of the fundamental mathematical operations are pretty easy. Add, subtract, multiply, and so on. Let's actually make use of this one time, just for fun, to make sure we really understand what it means. So imagine, as an example, that r has the specific value 1. So we are out here, say, r equals 1. If I make use of my series, that's going to give me the following. To find an approximation to the z-coordinate at this point. So to find that approximation, remember our series says using only 4 terms. 1 minus r plus r squared over 2 minus r cubed over 6. So when r has the value 1, I'm going to have the following. 1 minus 1 plus 1/2 minus 1/6 essentially. These two will cancel, and all that remains as the approximation is this quantity right here, 1/2 minus 1/6. In other words, let me zoom in even more here so you can understand that when r equals 1, the approximation is this. This is my approximation. This is what this represents. The actual z-coordinate itself would be equal to e to the negative first. If you find the value of e to the negative first and you find the value of 1/2 minus 1/6, you will see they're not exactly identical because the series is just an approximation, which means that over here, officially speaking, this would be my error. And how do you get rid of errors with series? Well, you add more terms because that would make the height of this little bar grow towards the z-coordinate at that point. In other words, you'd be getting rid of the error. But this is good enough for our purposes, just to get a feel for how things are behaving here. I'm going to zoom out. So I've zoomed out here so you can see everything. I hope this has been an interesting journey. I love mathematics. It's an absolutely fascinating subject. And you know, just when I think I've learned everything, there's always something new to be learned.